Erik Tonni from SISSA, who is going to talk about entanglement Hamiltonians in the presence of a bundle.
Thanks, Domenico. Thank you. First of all, I want to thank the organizer for having me here for such a long time, practically a large part of this program. It's been a great pleasure. Very inspiring period, very interesting, so thanks a lot for having me. And also thanks for giving me the opportunity today to speak about this work, about Entanglement Hamiltonians in the presence of a boundary, made over the past few years. So first of all, I have to acknowledge my long-standing collaborator, Michael Mincher. We have been working on this kind of problem from starting the COVID time and the past following year, and then more recently with these two brilliant young collaborators, Stefano Trezzi, who is now a PhD student in Barcelona. His work is what is undergraduate thesis, and then Christoph Mint, who is a postdoc now on a job market, so he did basically everything here, and so please pay attention to his application if you encounter it. Okay, so this is a work about Entanglement Hamiltonian. Let me motivate a little bit this work. So one go back to the original one of the motivation that make entanglement of quantum system attractive is that okay, if you're in a quantum system, somehow if you want to measure or do some experiment here in your lab, we are here, and you don't know, you want to say something about the rest, the complement. Particularly, you want to know whether outside there is a beautiful landscape, Newton tree like here, right? Or something like that. You don't know, right? If you, yeah, exactly. So, unfortunately, it's not like here, but anyway, the idea is that you can use entanglement to do something, to observe some quantity here and say something about what is outside. Okay, that's the idea. Of course, these are words you want to understand how is it possible, and so you go to the simplest case. In this talk, we consider this, let's say, this general question in a very simple system, 1 + 1, half line, and in our situation, the subsystem is just an interval, and the difference between the Newton trees and the Apple Jewish factory is basically the boundary condition here. Okay, so question is study something about entanglement here. So you trace out everything in the ground state, and you want to detect somehow or not which kind of boundary condition you have here. So very simple problem to understand. Good. So this is the outline of the talk. I will talk about Entanglement Hamiltonians. So first, in the first part, I will give you some background result about CFT2. Then I will focus on the explicit example of the massless Dirac field on the half line, which is a boundary CFT. Very simple. Then I will elaborate a little bit on this model by putting the same field on a segment, but with an inhomogeneous background. And in particular, we'll make some comparison with the lattice calculation on the rainbow chain. And then in the last part, this problem, the half line, is considered for the massive scalar field with Robin boundary condition, which are not conformal invariant boundary condition. Okay? So this is the simplest setup of everything, of most entanglement talks. So you basically take a quantum system, for instance, in the ground state, you bipartite the system like that, and you trace part of the Hilbert space. So even though you start from a pure state, this reduced density matrix is a mixed state, and therefore you can calculate the entanglement entropy with just the von Neumann entropy associated to this. Today we will focus not on the entanglement entropy, but on the operator itself, rho A, which is a reduced density matrix is a positive, semi-definite positive operator, so you can take the log of it, and the log of it is usually called Entanglement Hamiltonian in the condensed matter literature, but the concept has been taken from the algebraic QFT literature, where it is called modular Hamiltonian, with a little caveat that I explained. So then you can compute the spectrum of this operator, and then out of the spectrum you calculate the Rényi entropies, the moments, or the entanglement entropy in the usual way with the replica trick. Let me stress that this is a unitary, this object here generate an evolution, simply like a standard Hamiltonian, generate a time evolution. Now you can consider this evolution with tau reals. This is a kind of time, can be called modular time. And if you apply this unitary evolution to an operator, you generate a so-called modular flow. So this, since part of the audience is with my mathematician, then we certainly recognize that, so this object has been studied a lot in the context of algebraic quantum field theories. In particular, if you have von Neumann algebra observable associated, for instance, to a subregion, this omega is, you can think about the ground state of the system. Then what you can do, you can introduce this operator, which is called Tomita operator, is associated to any operator in the algebra. It's dagger, so very fundamental operator. And then you introduce the so-called polar decomposition of this operator, which allows you to write this operator in a unique way as a product composition of these two operators, delta and j, in a unique way. A naive comparison is with the complex number. Any complex number can be separated in phase and the modulus. So you have to think to this j as the phase and this delta as the modulus. This is an operator. And then these are the so-called modular object, modular operator, associated to the algebra and the state. So in this sense, Entanglement Hamiltonian, this is basically the Entanglement Hamiltonian, is very different from the standard physical Hamiltonian because it depends on the state you start with, and also on the bipartition, which is not true for the physical Hamiltonian, which does not care about the state, right? Okay, so these two operators preserve the vacuum, and then if you have an operator in the algebra, you can evolve with this delta, the modular operator, and generate a flow, okay? And then the famous Tomita-Takesaki theorem tells that this evolution, this modular flow, preserves the algebra and its commutant, and the J, the modular conjugation, allow you to jump between the algebra and its commutant. Last comment I have is that these two objects, sigma t, so this modular evolution, and j, could have geometric action or not. It's t, but so just to give you an example, very simple, that this is math, but when you go to physics, you want to have example. The standard example is the Rydberg wedge, okay, alpha of the system. This is sigma t, the evolution in this way, and then J is the one that associates here the algebra, here the commutant. J is the reflection with respect to the origin, sigma t evolves. This is an example. So this is the most mathematical slide I have. So let me go back a little bit to another motivation. So in the end, I want to understand some features of the bipartite entanglement that are not captured by entanglement entropy. Of course, people explore various quantities to do that. You can focus on a single state and consider this kind of problem. Or more recently, people study the case of two states and study, for instance, relative entropy or circuit complexity, how you go from a state to another. But in the end, you want to capture something that is not visible just through entanglement entropy. Today, I will focus on a natural way to go beyond entanglement entropy, which is just to go back in this chain. So when you compute entanglement entropy, in the end, you have this operator, you have a matrix, you compute the eigenvalues, and then you compute that. So of course, the information which is here is much more than the information which is here. It's just a number, this is a matrix. So you have information about the spectrum and the basis. So, but of course, this is much easier to calculate than this, so you have to compensate. Good, so the first part of the talk is about this operator in CFT2. This is the example I was mentioning. This is due to Bisognano-Wickman, famous theorem in the 70s, stating that if you have a relativistic UFT in its ground state and the subsystem is alpha the space, okay, the Entanglement Hamiltonian can be written in this way, in this form, and then this is something I have to stress. This Ka is not fully relative to the, is not equally to the delta of the algebraic UFT people, because the delta, in order to construct the delta, you have to consider both A and its complement. So if you consider Ka here and its complement, you see that this becomes exactly the generator of the Lorentz boost. That's why the evolution is the one that you know from the Undu effect. Okay, in this case, we are lucky. The modular evolution and J have geometric action, Lorentz boost and reflection here. Then, if you are in CFT in the ground state, Islop Longo in the 82 and then more recently Casini-Huerta-Meyer study the problem of the modular Hamiltonian of a ball of radius r, and you get this expression where T00 in energy density, and this is a weight function that knows about the geometry of the region and the state. This is the ground state. This is the one-dimensional case of the interval, becomes this simple parabola. In general, I will show you an example. There are a class of cases where you can write this operator in this form, which is again energy density, but you have to integrate over a weight function, which is sometimes called entanglement entropies, just because it's the usual. If you think these are the inverse temperature, sorry, entanglement temperature. If you think this beta is inverse temperature, depending on the position, but this interpretation can be misleading. But I will show today also other important cases where this Ka is non-local. Okay, so this is a local expression in the sense that you integrate a local operator on some domain, eventually with some weight function, which contains a lot of information, but it's a local operator. Okay, I will show other examples. Let me review this approach to the entanglement entropy entanglement spectrum. Basically, the idea here, this is based on BCFT, and this is the Euclidean complex plane. Is a similar setup that Masaki discussed yesterday, but different approach. So here is the system. The idea here is that you can regularize the theory by cutting out the little disk around the endpoint, and then you get an annulus basically here, and then you can map the entire plane into an annulus like this through a conformal transformation. And if you do that, then the Rényi entropies, the moments of the reduced density matrix, can be calculated through this ratio. This is a partition function of the n annulus, which is obtained by cutting along this line and joining n copies, okay, and normalized in such a way for any little n equal 1, this is 1. And if you do that, and then you consider this epsilon, this UV regularity, which is 0, which corresponds to large W, you get the standard expression that Masaki discussed yesterday. This WA is depends on the situation that you consider. In the ground state, it's just log L over epsilon. And the extra information you get from this approach is that the subleading pieces are related to the Affleck-Ludwig boundary entropy associated to these boundaries. Okay, this is the overlap between the boundary state with the ground state that you put here and there. Okay. And if you look a little bit into this expression, you recognize that you can express the entanglement spectrum of this reduced density matrix in terms, this is an expansion in the UV cutoff, this is log L over epsilon, in terms of the CFT quantity, no? So this is the central charge, and these are the primaries of the BCFT, primary and descendant. This WA depends on the situation, but if you have the ground state, it's just log L over epsilon. So this is the leading term, this is a constant term, this is subleading. Good, so you see that of course the spectrum contains more information than entanglement entropy, no? This is the conformal dimension of your operator, which are not written here. You get it, well, if you take the difference, consider the entanglement gaps and the ratio, it's immediate from this expression. You see that the difference, select this piece, and the ratio cancel this part. You get a UV finite ratio on the conformal dimension. So looking at the spectrum, you have access to the BCFT spectrum of your underlying CFT. Of course, you can ask which, yes?
J labels the eigenvalues of the...
Yes, J labeled, yeah, sorry, this is wrong. No, yeah, this is labels the eigenvalue of the reduced density matrix.
Right.
And here it's associated to the, not to the primaries, this is also, include also the descendant.
But these are the real delta J's of the CFT.
Yes, of the BCFT.
Of the BCFT.
BCFT because it comes from the partition function on the annulus. So the sum, basically you write this sum, the sum that enters here, term by term, you can extract this expression. Okay, good. Let me give you an explicit example. Explicit example is ground state inter on the infinity line. So this is the complex plane. You cut a little disk here, and then you map first on the unit disk and then on the annulus. This is the map, and you get the expression of Islop Longo, and then you calculate entropies in this way. But of course, this is a conference about boundaries and defects. So we are interested in what happens if you have a physical boundary. This is a physical boundary here. This is the interval attached to the boundary. You play the same game. Now the important difference is that you can have different boundary conditions here. This is the physical boundary condition. This is the boundary condition at the entangling point. And indeed, you get this expression where now you may have a GA different from GB. This is just to tell you that these are all local expressions. This is an example not with the boundary on the circle, but if you change the conformal map, this changes the explicit expression of the weight function here. This is another example of a finite interval at finite temperature, but on the line, and you see this expression here gets more complicated, and most importantly, it gets a dependence on the kind of state that you are considering. Any question? This is the end of the universal part. So,
sorry, could you?
Yes.
So you have G small a and G small b in the previous expression.
Here, yes.
GA corresponds to the entanglement cut.
Yes, this is. Yes, A, B here, A and B, yes. These are two, yes.
So one is from
one is associated to the physical, the boundary state that you choose, and the other is associated to the induced, let's say, boundary state induced by the cut.
Entanglement cut.
Exactly, yes. Yeah, this is kind of different what you discuss, but again, we have to use BCFT, and let me stress that the previous expression for the entanglement gap has been checked with lattice model, and it agrees with the fact that here there are Neumanns, so free somehow for some reason when you cut. Yes.
Can you remind, if you do just a cut, what is the boundary condition that is induced by?
Yeah, exactly. That's a good question. It's Neumann. Neumann. Why? Don't know.
Okay, and it's not understood why this is the case.
No. This comes from the numerics. Yeah, if you typically this we did, for instance, for harmonic chain. You study this case, and you change the bound. You can, for instance, for a free boson, not free boson, but harmonic chain. You can choose either Dirichlet or Neumann, and then you compare the spectrum, and you see that this is given by, and here it's compatible with Neumann boundary condition here. Naively, you say you cut, and so you are free, free end naively, but. Yeah, it would be nice to understand why, or people studying symmetry resolve, for instance, they put some extra flux here, so you modify, but yeah, anyway, yes, that comes from the observation, but the BCFT does not tell which kind of boundary condition you, so just tell the dependence, yeah, it's not universal information. Look good, so now, we consider an explicit case, the master Dirac field on the half line, so first let me remind the model, very well known to this audience, but just to be quick. So the master Dirac fermion, yes, no, okay, it's a doublet of complex field like that. This is the equation of motion, conservation of energy, and let me stress that there are two different U1s in this theory. Right, and that acts on the fields like that. You see R are the two components of this doublet, and the vector U1 and the axial U1. Okay, and the important things that I want to stress is that if you consider this theory on the line, both the U1 are symmetries of the theory. Okay. Then you quantize the theory in the standard way, anti-commutation, imposed anti-commutation relation, and this is the free theory, so everything boils down from the two-point function of these two sets of fields that are completely decoupled here. No? So this is the two-point function of the free fermion that you know, this is the chiral, and you see there's psi 1, psi 2 is 0, because you are on the line. So then let me tell you what happens. Casini and Huerta some time ago studied this problem of the modular Hamiltonian of two disjoint intervals for the free fermion on the ground state. And in this case, so they found the result for any number of intervals, very general, but I want to tell you for this case, two symmetric intervals with respect to the origin. So you have only two parameters that, right, and the point is that now, this is one of the main messages I want to give you, now the modular Hamiltonian is not local anymore. In particular, there is a local term here, which again involves the energy density of the free fermion with a proper weight function, but most importantly, there is an extra term which is bilocal. Bilocal in the sense, this is the definition, in the sense that depends on 2 points. No? Put t equals 0 for simplicity, x and y are 2 points. You see psi 1 is evaluated on x, psi 1 is evaluated on y. There are 2 points, but in this problem, these 2 points are related in a specific way. So in particular, in this symmetric setup, the relation between this value, xc conjugate for some reason, but is equal to the inverse of x. So in particular, if you have a point x here, x conjugate, there is a minus, so it's on the other interval. Right, so this is a bilocal operator because see, it involves 2 fields evaluated on the different interval. So in this sense, but still is bilocal, right? But still there is one integral here, no? Not 2. So you have to integrate over the red part, and then, but taking into account that this operator is made by, it's a quadratic operator because it's a free theory, but the fields are evaluated on different points. So this is a new kind of something that we are not used in standard quantum field theory to deal with this object, but it's the natural thing that emerges in this simple model.
Is there an intuitive way to understand why you get this conjugate point?
Intuitive? No, I don't tell it.
You may have expected the double integral, as you say, so why does it localize?
Why, you mean, why, for instance, why this expression
why it
here?
localizes on this conjugate?
I know the mathematical reason, but the physical, intuitive why is like that, I don't know. Yes. But it's...
Because you do have, clearly here, the reflection symmetry is important, right?
No, exactly. No, exactly. This I choose this because it's important later. Here you don't have reflection, so this point can be 4 points, 4 generic points, and then this expression becomes more complicated. Becomes something like this: xc equals some r0, some c0 plus x minus c0 square. Yes. And then this expression, it's an inversion, but these two numbers can be written in terms of the 4 endpoints, so it's very generic. It's an inversion. But, right, yes?
If you were to do it, say, in calculation theory for interactive theory, would you have like a multi-local term? How many integrals would there be? Is there some regularity?
No, I don't know, because this calculation is strictly related to free fermion. Nobody knows how to perturb, how to do anything. It's really, this is based on the Peschel formula, which is calculated for the free field, quadratic theories. We don't have a treatment for the interacting fields.
If I folded with the inversions, then it would be local.
No, if you wait a little bit, I'll do that in one slide. Yeah, this is but let me start. This is a specific example suited for the half integral that I will consider now. But in general, this is the situation. So you have 4 points, and then everything depends on 4 points. If you have 3 intervals with different length, the expression is similar. Yeah, maybe it's related to Marco's question. If you have 3 intervals, for instance, you have again a bilocal field, but any x has another images in another interval. But the operator is still bilocal. So you have to sum over the intervals. This is I choose this because the sum, discrete sum, is just one term, the other one. But if you have 3 intervals, you have 2 terms. One with x conjugate is here, and then there is x conjugate.
I just meant if you map them so the intervals are identical, then it's local. It's in 2 sets of fermions.
No, here this you don't get. Yeah, again, I will do that. So if you wait a little bit, you can ask me again. Yeah, because the half line case is obtained precisely by making this reflection idea. So here, let me stress again that you have these 2 U1s, and they are both preserved by, you can see that these 2 expressions preserve the 2 U1. So Casini and Huerta found this expression by solving a spectral problem I will discuss. And then immediately later, Longo, Martinetti, Reren proved that the correlators generated by these operator satisfy the KMS condition, and this supports the calculation of that. So again, the two chiral fields are decoupled. So that's why you can treat 2 chiral theories separately on the line. But now now we like boundaries, so let's put a boundary in the problem. Consider the same model on the half line. This is the Cardy condition that people discuss a lot in this conference. So no energy flow through the boundary. If you study in this simple model, this Cardy condition, you discover that this model, there are 2 phases. Basically, you break one of the 2 U1s. So you have the vector phase by imposing boundary conditions. So the solution of this Cardy condition in this model is given by these 2 solutions, these 2 different boundary conditions, which preserve either the vector symmetry or the axial symmetry. So you have to choose. And importantly, now you see that the boundary condition couple the 2 chiralities. So you cannot treat, like on the line, the theory in a chiral way, because the boundary condition, chiral, you have to consider the full CFT, okay? And then you have two different phases here to consider, so these parameters enter in the game, and these correspond to the tree or the factory that I was mentioning before. So these are the boundary conditions that in the problem, okay? This is a free theory, so everything boils down from the two-point function, and this is a slide just to tell you that I can treat the two cases in a unified way, but everything boils down from the two-point function. This C is the distribution that I showed before. So now let us consider your interval here, not attached to the bar. Yes?
What were these alphas?
Alpha is a phase.
Yeah, but what? You choose whatever you want, or?
Yeah, between 0 and 2 pi.
So you can choose them the same for both cases?
Yes, but you have no reason. No, the point, no, let me stress. These two, what is important is that here you couple psi 1, psi 2, here psi 1 at 0, and psi 2 star. That's the important, that's the key difference between these two boundary conditions. And then these two numbers are independent, because once you impose this boundary condition, I call it alpha vector and alpha axial. Yeah, you can choose whatever you want here, and you are guaranteed that the Cardi condition is satisfied. So this is one parameter that you have in your problem. Yeah, this is important because I will show you that in this example, the entanglement entropy does not depend on the alpha, but the modular Hamiltonian it does. So that's.
Is there like a unity transformation that changes this alpha? Is that
no. This you fix. No, if you
or?
change alpha, you are changing the boundary condition. It's like you have a parameter. Like in Robin case, you have one parameter. Yeah, this defines the model, right? So you choose at the very beginning, and then you bring this number with you until the end, and then you can ask whether this number influence or not. So this is really the solution of the Cardi condition in this explicit model. So. Right.
Sorry, but how can the bulk has a symmetry, right? So in the bulk I can change alpha. Just in
no, in the bulk there's no alpha. The two are decoupled. That's the point. In the bulk, no. What's alpha in the bulk? This is the boundary condition. So, like any boundary condition, you can have a parameter that.
No. But what I mean is I can do a chiral transformation on one of the fermions.
Chiral transformation? I don't know. What do you mean? Chiral transformation?
Is there an axial symmetry that I can do in the bulk that will...
Yeah, exactly. This is, if you impose the boundary condition, yeah, you can change both U1. You see that if you change U1 the same way, you preserve the U1, but you don't... Basically what you're thinking, I can change the phase of psi 1 and psi 2, but this alpha v is there. It's obvious. Now, if you multiply this by the same phase here, you don't, alpha v is not affected.
Right, but if I multiply by a different phase?
It's not a symmetry. It's not a symmetry of the theory.
You can think of it as a field redefinition?
Sorry?
You could think of it maybe as a field redefinition.
No, because these are, yeah, we explored this possibility in the paper, but this changed the asymptotic states of the, in the positive infinity. For instance, if you do scattering, if you redefine the field, then you have to change again the fields at infinity in the scattering. Yeah, it's really, you have to play with, you have to deal with it, like any boundary condition. You define at the beginning and you keep with you.
Yeah, physically, I think this left vector boundary condition just means that you shoot left move fermion to the boundary, then it's bounced back as a right moving fermion. But in the actual, the right hand side boundary condition, you shoot left moving fermion, then it's bounced back as antiparticles.
Yeah, exactly. That's the. Yeah, it's really a different boundary condition. So.
And if you take an infinite system and you take a finite interval, which boundary conditions are used?
Yes, I will consider later the segment, but the short answer is that if you can choose both. Yeah, you can choose The simplest case, you choose both, the same. But you can decide to keep mixed boundary condition. That's interesting. It's an interesting problem. If you're on the segment, yeah, later.
If you're on the segment, you don't have to choose boundary conditions. You just say, this is my segment.
No.
You don't choose your regulator somehow.
I mean, if you are on the segment, you have to choose the boundary condition at the end of the segment. I don't.
In the previous discussion you had, you said, okay, if I kind of take an infinite chain and I just take something, then I get the normal boundary conditions. And you said that you didn't understand why.
No, but this I said with entanglement. So there's no entanglement here.
That's what I'm asking. If you kind of now consider entanglement in an interval?
No, if you not consider entanglement, you decide your model at the very beginning, like any BQFT, any model with boundaries, you decide which are the...
Yeah, but there's no boundaries in the Dirac case. And you take an interval and
on the line, you
yes.
mean? No, in that case, there's no boundary, you don't have boundary condition to choose.
And you calculate the entanglement entropy for an interval.
When you calculate the entanglement entropy, then you introduce some auxiliary boundary, let's say, and then it's, yeah, that's this cutting procedure induces some boundary condition. It's not something that you choose, but here it's different. You choose from the very beginning, and if you change the boundary condition, are different models, okay? Right. Good. So then you study this example here. I have to be quick here, so believe me. So this is a quadratic theory. So the modular Hamiltonian of this interval is a quadratic operator like that. And this is the Peschel formula adapted in the continuum. So the idea is that this is the formula that Peschel found on the lattice. But Casini-Huerta using the continuum, so this is a two-point function. You have to understand it as a kernel, restricted to the subsystem, and then you have to calculate these objects. So the question is whether this kernel here is local or not. It's just a bunch of delta function, or it's a non-local object. Right, so let me be quick on the procedure. So you have to solve the spectral problem associated to this kernel. And yes, believe me, in the end, the result is this one. So even on the half line, it's a bilocal object in this form. So now the local term is again the energy density integrated on the interval. Now it's a single interval, not two interval. And the B is this one. You see, depends on A and B. But the interesting thing is the bilocal object here. Now, the bilocal point is given by this expression, just like the previous one, except for the minus. So, if you have a point here, the x tilde x conjugate is in the same interval, and right. And now the bilocal object, the bilocal operator, depends explicitly on the alpha that you choose here. Explicitly, right? And okay, this is the expression that you get here, and the interesting thing is that, so x tilde now is inside A. And if you want, this is, I hope, give some intuition to Gerard's question. So this problem is solved by using the mirror symmetry. And indeed, you see the mirror reflection symmetry, mirror symmetry, much more deep, but x tilde, you see, is just the previous one, just with minus. But now, your conjugate point is inside the interval, no? So if you're, and this implies that there is also a self-conjugate point, which is the geometric mean between these two endpoints. This means that, okay, why you say, okay, so this is an explicit dependence on the boundary condition. And so more explicitly, you can write in the two phases, this is the expression, and you can check that in the vector phase, axial phases, these two expressions preserve the corresponding E1 symmetry. Remember this E1, you multiply by a phase that Marco was mentioning. Yeah, you can check that this one preserves the E1 vector and breaks the E1 axial, and the opposite for this. And this is because of this dagger, no? Here there is a dagger, here there's no dagger. But okay, this is expected. If you compare this object with the expression of Casini-Huerta on the line, this expression preserves both the U1, and of course there's no signal of the boundary, right? Here there is explicit dependence here on the boundary condition of this real number that you have to choose. And now you say, okay, this is an operator, I compute the entanglement entropy. Yes?
Where's the dependence on your boundary conditions at the ends of the interval?
No, here, no, that is not here, yes. There's no, yeah, here you don't see. Like, if you want, it's in the, yeah, this is a good point. It's like when you write, this expression, T00, this object here, you can integrate on A, is something in the bulk, but the boundary condition is here. So the boundary condition is in the fields. This is the example of Hislop long, no? On the sphere, you can say, what is this T00? T00? Ah, sorry. Yeah, you have expression like this. Here you don't see any boundary tab, nothing. But this guy is a boundary. For instance, this is the expression here, no? If A is here, in a BCFT, no? Sorry, this is L, this is L, this is L, except for factor of 2. Here, A is here, but where is the dependence on the boundary? In T00, because your energy density is made by fields that satisfy boundary condition, but here you don't see. But I agree that.
Sorry, I just thought that at the end of the intervals I had to do some regulator, which would be equivalent to a boundary.
Yeah, the point is that here you don't need to regulate.
Oh, okay.
Yes, thanks. Yeah, that's the. Yeah, when here is a completely, yeah, you don't regulate. When you calculate entanglement entropy, basically you have to calculate the integral of this guy 1 over, and you have to regulate here, otherwise it's infinite. But here, don't need to regulate. Yes, yeah. Right, so if you yeah, this is the answer. Maybe this helps to answer. Yeah, it is a calculation that Gerard was asking for. This is a BCFT. For any BCFT, for the setup of the interval separated, the expression like this is the central charge, and this is a 2-point function of twist field. It's very complicated. It's like a 4-point function that bootstrap people are considering. Yeah, I think Marco talked about this kind of function, but yeah, in general, you don't know this function of the harmonic ratio, but in this case, you know it's a free model, so you can calculate. This is the method based on the spectrum, and if you do that, this is the epsilon that you need to introduce here, otherwise it's infinite. You make this calculation, you find that this function is identically 1. And most importantly, there's no dependent on the alpha here. So, this is an example, very simple, of where the modular Hamiltonian knows about the boundary condition, the entanglement entropy does not know, because in this product, it cancels. That's the technical reason. But, yeah, in the philosophy that entanglement entropy is not enough, you have to consider more complicated objects. These are special bipartition where the operator becomes local when in the interval is very far, yeah, everything is okay. And then let me stress this story of the modular flow. So as I said, this is a unitary operator, so the modular flow is defined like that. You can study the modular flow of the field, of the two fields, and this is what happens. So you have to look at, for instance, if I start with a field here and I see the evolution, the modular evolution, this is the trajectory. Together with this trajectory, there is a conjugate trajectory. We start from here, which is the dash one, which boils down in the same inside the interval. And this is the same phenomenon that happened in the two interval case, with the exception that in the two interval case, one trajectory is here, the other trajectory is in the other lab. When you have the boundary, because of the reflection story, etc., this boundary reflect the phenomenon. You get another trajectory. Of course, you have to see the expression, but believe me. Right, so importantly, the conjugate model is inside here, and then this object depends also on the kind of boundary condition you have here. So in some sense, yeah, let me tell you, suppose you are here, your lab is this interval, you don't know that there is the tree over there, no? Then you see what you do, you let evolve your field with the modular Hamiltonian, okay? If the boundary was not there, you don't see anything, just a local evolution like that, the green there. But because of the boundary is there, you see another evolution popping up over there, in the same lab. And this is depending on the boundary condition, yes.
Your operator becomes bilocal.
Yes, exactly. Yes, yes. And that's because the Hamiltonian has a bilocal term. And so the evolution, the effect of the evolution, you can really see in the equation, but this is the geometric, this is the geometric flow that, in this case, the geometric action of the is given by this plus this. If you choose instead this point, is the blue plus the green, and this is the self-conjugate. So the two things can collapse. But yeah, this is just to, this is a signal that tells you, okay, there is a boundary outside there, and it's a physical effect that I see that entanglement does not tell you, because entanglement does not even depend on the boundary condition that you have here. Entanglement entropies. But this is entanglement Hamiltonian, so it's more complicated, more rich, and yes.
But this modular Hamiltonian depended on the boundary conditions or not?
Sorry?
So if you want to evolve it with this, you have to know.
Yeah, that's depend on alpha, exactly. That means that this flow, you have to shoot the field. This is just a line. But if you see the field expression, it contains also the boundary condition. I have a slide if you want, I can show you, but it's really.
But what Hamiltonian do you use to evolve this?
The modular Hamiltonian.
Yeah, but for the modular Hamiltonian, you need to know what the boundary field is.
Yes, you start you start with the boundary condition, of course. Yeah, no, I see what you mean. Right, I see what you mean. But you start with a system, no, and then you trace out. Yeah, you assume that. Yes, of course. The system is underlying everything, and so somebody decided the boundary condition. But yeah, I'm just telling that if you just stay inside here, you see everything outside. What is everything outside? Even if you do, that's the only thing. It's in a complicated way, but right. Yeah, everything here is for the ground state. If you change the state, underlying state, everything here changes. So. But this tells that if you look at the modular evolution, here you see everything, more or less. Right.
Sorry, do you assume your interval far away from the boundary?
Any distance.
Any distance. But there could be some channel, this twist orbiter first fused with the boundary. In that case,
yeah, if you get close, it becomes local again. If you get very far, it becomes the thing on the line. Yeah, you can look at this channel, but... Now here there's no twist field. If you think in terms of twist field, you get confused. Yeah, forget the twist field here. Right, very little time, sorry, it's my fault, but I will go quick here.
Sorry, for the first part, can you also set the boundary condition to preserve left or right?
Left or right?
Rather than vector or axial.
Yeah, you can have the other, yeah, you can do that, and it's just change the bilocal. Yeah, this expression. Yeah. So this, we'll go quick, is the work done with Stefano Trezzi. The same problem on the segment, which is what was asked before. But with the same boundary condition, you can map the problem to the previous result, to this case, using conformal map. And now the size of the segment start entering. You see the expression is pretty complicated, so I don't bother you, but the entanglement entropies can be computed by taking the inverse of this and integrate. on the regulated. It is another way based on the contour function. Anyway, then you can also put a background here to consider your field theory while factor. This case can be also addressed. There are motivation, and we did that here. And these things, the same structure, but the weight function changes. And here, this is Frank's question. Here you have the two boundaries, which is the same boundary condition, the same alpha, because we want life simple. If you want to have axial and vector here, very interesting. We don't know what to do. Typically you have to introduce BCCO, boundary changing that Masaki talked about, because this geometry can be mapped on the disk, and then it's clear there that you have to introduce this operator. So in terms of entanglement entropy, it becomes a 4-point function, 2 in the bulk and 2 in the boundary. So this is the expression, very complicated, let me not come, but what I want to stress is that, okay, this is something you do in field theory, but what happens, there are lattice models behind this expression. I will focus on this one, which I like. It's the rainbow chain, studied a lot by Italiano, Latorre, Sierra, collaborator. This is a homogeneous chain, a free chain. You see this opening depends on this parameter here, h. For h equals 0 is the free fermion on the segment, but for large h, the ground state becomes a valence bond state, and this is a great simplification because the entanglement entropy of an interval at here becomes a volume law. That's why this model is interesting. It's not an area law, it's volume law, even though you are at criticality. Then the underlying inhomogeneous background is given by this while factor. So it's an ADS2 with a singularity in the center. Okay, so this is the Ricci scalar, constant negative, and then there is a delta in the segment. So then there is a special point in the middle, and you can choose various configurations for your interval. And then at large inhomogeneity, you count the entanglement entropy, you just count the cuts, no? Like in any valence bond state. So in particular, you have to count the bond that goes from inside to outside. And then in particular, here there's no bond that everything stays outside or overlaps, so you expect zero entropy. Zero entropy in this case. No. Then you can say, I can study this object on the lattice. And this is an example for two disjoint block on the line. This is the matrix, so this is the Entanglement Hamiltonian, it's a quadratic model, but what is this H? Is this matrix here. Very complicated, long range and inhomogeneous. This is the off diagonal block when you increase the distance. Now what happened in our case? Well, this is the Entanglement Hamiltonian matrix for zero inhomogeneity, so on the segment, you see you have to fold this kind of local thing. So when you have a boundary, now everything is on the same thing, but both local and non-local terms are in the same matrix. And this is what you see. But you see this line here is given precisely by the conjugate point that I was telling before. And then if you increase the inhomogeneity, this front bends. This is an example for this bipartition, the singularity is here, and you see that if you increase the inhomogeneity, you see this cloud around the singularity, these fronts. So this is a lattice model. Then you have to do the proper continuum limit, and this is the thing on the lattice. These are lattice point, and the solid line is the CFT that I was showing, so perfect agreement for the local term here. And you see that if you increase, this is the homogeneous case, the fermion on the segment, homogeneous, and then if you increase the inhomogeneity, you see this plateau gives you this volume law behavior. Then if you change this, you see the difference between the role of this singularity pops up in the local term. And the same thing is in the bilocal term. I will go quick. Then you can also study the case when you can study both the systems, so inside and outside. And you can study the same analysis, of course, some numerical issue. So if I have 2 more minutes, yeah, it's a pity that, yes, if you give me 3 more minutes, thanks, 5. Anyway, the last part I want to tell you about this work done with Mintz about the massive scalar field on the half line with Robin boundary condition. I will be quick, but so this is the field theory that yeah, we as a boundary, it's a kind of standard prototype of the boundary QFT. Massive scalar on the half line with a Robin boundary condition here at the origin, right? So now you have a parameter, and only for Dirichlet or Neumann is conformal, right? In the rest is you break conformal invariance, so you have to okay. Theory and a massless case, I refer to this interesting paper, but here we use we want to study the modular Hamiltonian in this model. We used this old result by Figliolini Guido, based on this expression for the modular Hamiltonian. This is D is the Dirac, the Klein, yes, the differential operator, the D square minus plus M square. You have to consider this as a kernel. You have to this technical part. The subsystem enters in this projection here. Okay, and this is a numerical method first introduced here by Christoph, Bostrom, Kadamuro on the line and in Minkowski 3+1 for the sphere. We adapt it to the half line. The idea is that you have to introduce some set of functions to discretize. These are the red one, and then you have to smear here with the blue one. And this is the scheme to solve. So this is the ideal QFT computation you want to do. First, you start from here. You find analytic expression, and then you integrate with the test function. This is what you would like to do, but you cannot. We are not able to do that. So you have to go through this numerical procedure here. Here there are matrices, and then you find this kind of object. This is the raw data here for interval here and the complement, and here when you smeared with the test function. Okay, I will go quick. So this is what you get from the interval attached. Just to a benchmark that you get this object that you expect from BCFT, Dirichlet and Neumann. But then interesting case happen when you consider Robin boundary condition. Because from our numerics, you see Robin, when you change the Robin parameter, the numerical data does not collapse on the parabola. And this, and then this is we interpret it as a signal of non-locality. And this, another hint is when you consider the anti-diagonal here. So this object is along the diagonal, this is anti-diagonal. When you compare with the BCFT result, you see that the Dirichlet, for instance, collapses to 0. But the other cases, the numerical data does not arrive to 0. And this could be a footprint of the fact that in this case, so when you break conformal invariances, this operator is not local anymore. And this is the message I want to give you.
Could you remind me what was Robin boundary condition?
Ah, sorry. Robin is this one. This one. So d phi equal eta phi. So for eta equals 0 is Neumann, eta infinity is Dirichlet, and in the middle is not conformal.
Thank
you. Good. Right. Again, we study the mass dependence, and this is the case, most complicated case, but we observe a nice behavior when the mass is very large. When the mass is very large, you go from the parabola to this Bisoniano-Wickman behavior, and then it could become local again. This is in agreement with calculation, similar calculation on free lattice. And then let me tell you what happens at the level. Yeah, you see this is the matrix, the numerical data. When zero mass, large mass, you see that here everything is non-local. Okay, we can discuss this in private. The final message is that in this case, except for the conformal invariant, we think that everything is non-local. Unfortunately, we don't have analytic prediction. This is future work, but right. This is the main message I want to give you is that okay, even exploring free QFT, this is we study only free QFT, but this operator sorry, this operator, modular Hamiltonian, this is the typical expression for free mod, so quadratic, but the point is the form of this kernel. I gave you example where this kernel is local, like in CFT in this case, okay, in that case it's even non-quadratic, but bilocal, free fermion, or fully non-local, free scalar. So the message is that, yeah, there are these beasts emerging in entanglement. It's very simple setup. So if you are a QFT person, this is the typical situation. We are not used to deal with this kind of model, at least not. But yeah, you can explore this various directions for future cases. But in general, it would be interesting and very insightful to find analytic expression for these kernels. There are very few on the market. Let me point out this nice work by Casini, Huerta, and Spuntello, where they study this problem, the chiral current, and found a fully non-local object. So chiral current is just dphi, so zero mass, very simple, on the line, 2 interval, fully non-local. So if you ask for gauge theory or interacting model, I expect increasing complication, but more physics, more and more to find. So let me conclude by advertising that next year we are going to have some interesting meeting with algebraic and QFT people in Trieste. I hope to see you there. Okay, thank you.
Please. Can you use some doubling trick to transform boundary CFT to some? You can use doubling trick.
Yeah, we use doubling trick to find the expression.
To understand why this is
the doubling trick to argue the ansatz for the solution, and then to solve, yeah, you have to plug in this alpha. That's the interesting thing. But yeah, the idea is to use the doubling trick, and then in the doubling trick, see the role of the boundary condition, as usual in BCFTs. BCFTs is not only doubling trick.
So what is the basic reason to distinguish biological or fully non-local?
Yeah, I don't know. Yeah, I don't have a principle. This is something that Chris asked me some years ago, and I don't in some study, yes, a meeting that we had with Sergei tools. But yeah, there's no principle as far. Yeah, it would be nice to understand from scratch. Given a theory, is the time local or bilocal? I don't know. These are 2 examples of free theories. The Dirac field is bilocal. The free scalar is non-local. They are both C equal 1, and the mass is, yes.
Oh yeah, maybe the same question, but for the Dirac fermion with a boundary and you consider the modular Hamiltonian for 1 interval, you can map this problem by unfolding to the previous case, I guess. You unfold, you have a
yeah, but if you do that, you don't see alpha, yeah.
But I think that by unfolding, you define the field on the other side. I thought you can be good.
No, let's say that with this reflection trick, you can get the same weight functions. These are the same of Casini-Huerta in the symmetric case, but they don't depend on alpha. You don't get the operator.
Yeah, maybe.
Yeah, the operator is always like this thing you get by folding this function, but this one, yeah, the bilocal, yeah, it's not. Yeah, maybe you can use some trick, but it must be done carefully.
Okay.
Erik, there is this general Risch-Leader thing.
Yes, yes.
So in a sense, this is a special application, but one can ask the question the other way around. What information does the modular Hamiltonian allow me to access? Because if you allow me all the operators in the interval, I can access everything outside.
Yeah.
So in a sense, have you asked the opposite question? What kind of information I can access by just thinking about KA?
Yeah, I don't know, but yeah, this is a deep question, of course, because yeah. Here is just, you know, right, it's free theory, so yeah, this information on boundary condition, modular flow, it's a hint, but outside, no, I know that there is this theorem, but how to actually use it in this context is an interesting question, yeah.
But it feels that this has to do with, like, can you hear the shape of the drum? Now, here you only have information about the eigenvalues, and I think in this theorem you have access to everything. So here, the question is, if I only know the eigenvalues, can I reproduce the whole geometry of my system?
That would be amazing. I think that
Yeah, the point is that here, all the spectrum, they know about, of course, it's like entanglement. They know the ground state, the state of the entire system. They know everything, no? The geometry of the bipartition. Yes, the point is how to inverse, no, you have to invert. In the first part, I was giving an example. If you know the spectrum, if somebody gives me an entanglement spectrum, I can get the BCFT spectrum. Pretty easy, interesting, no? Then many people was one motivation on entanglement entropy. Oh, I can measure the central charge. This is what Frank did when you, if you have a new model, what is the central charge? You see the entanglement entropy and you measure the central charge. Well, here if you look at the entanglement spectrum, if it's a BSCFT, you can see the CFT spectrum. Yeah, there are other ways like, yes.
In this example at the beginning with the Dirac fermion, you showed these two trajectories that come from the.
Yes.
But if you were to look at the eigenvalues or some other properties of the Hamiltonian, can you see the alpha dependence or distinguish between the U1 vector, U1x, U1 right?
Yeah, to see the alpha, you have to consider the eigenfunction. Because if you do the spectral decomposition, you need eigenvalue and eigenfunction. Eigenvalue do not depend on alpha. That's why entropy is blind to alpha. But eigenfunction, they do depend on alpha, and that's why when you write the modular Hamiltonian in the spectral decomposition, you do see this dependence, technically. And then the evolution generated, bring back this dependence. Somehow the modular flow is richer than entanglement entropy because it sees the eigenfunction. That's the message. In the end, this game is about really distinguishing what information is encoded in the eigenfunction that are not in the eigenvalues. That's something
Okay, if there are no more questions, let's thank the speaker again.
Thank you.